Hello, welcome to the 12th live session of of Algebra 1 course. Um, this is not the last live session. The last live session will be on the next Friday. Okay. So this is just for one information if you need. Okay. So first, let me introduce myself. This is Shavik, and I'm doing a PhD on Starship Mathematics. So first today we will okay, so last day we were doing um, tensor products. Okay, so today also we will continue the tensor product. So let's recall the working properties of tensor products, and then we shall uh, dig. Okay, so suppose M and N are both R modules. Yeah, okay. Then we have something n tensor n, which is another R module and generated by M tensor small n. M belongs to M belongs to n. M belongs to M. Okay. So once again, so any element of M cross n is basically the linear combination of AI Mi cross AI. So finite. Okay. Got it. So this is one thing which is, and also so in tensor group the following properties: x tensor y plus z is nothing but x tensor y plus x tensor z. Secondly, x plus y tensor z is equal to x tensor z plus y tensor z. Okay. Third, x tensor y is equal to a into x tensor y is equal to x tensor y. This property holds for all x, y, z in a way, and most possibly these are the working what I should say. These are the working tools for the tensor product. Okay. Yeah. So And also one more thing we have discussed, the universal property. What is this? This is the following. Um, Suppose we have some m cross n to some p bilinear map we have with some bilinear map. Okay. Then, if this map is bilinear, then there exists unique linear map from where to where m tensor n to p, such that this linear map f tilde m tensor n is equal to f of jump from line. Okay. So this is one universal property. Okay. And also 0 tensor A is equal to 0, A tensor 0 is equal to 0. Okay. These are some basic things. So suppose consider okay. mm, now let's get into the proofs, the properties of tensor product. Okay. So hmm, so suppose so basically the thing is, suppose you need to show something reinforcement over isomorphism not. Okay. So for the you need to make a bilinear map. So directly it is not good way to do. First you need to make a map from m cross n to that ring. Then check that the bilinear. Then the bilinear will induce a well-defined map. Okay. So this is the one way of doing that. For example, so let m be our module. Okay. Then R tensor and R isomorphic to M as R module. Okay. Let's prove this. So first of all, how to do it? Yeah, it's model R model. So now question is how to do this. Okay. So for that, what we do first, we will define a map R cross M to M. Okay. That is Rn equals to Rn. And it is not difficult to check this map if is bilinear, as R1 plus R2 dot M is R1 M plus R2 M due to the module structure. and r comma m1 plus m2 is equal to r dot m1 plus r dot m2. Okay, and also r1 r2 m is equal to r1 of r2 m. Okay, so this induces a bilinear r tensor m to n f tilde, smaller tensor small m is denoted by r. This is a well-defined linear map. Okay, now the so this is one direction. Now we need to isomer. So we need to get a map of the reverse direction. So we get political map m to r tensor. A small m2 goes to one tensor small m. Sorry, one tensor small m. Yeah, we're putting it one tensor small m. Okay, so call it. Now observe that f tilde g of m f tilde of one tensor. By definition, this is one dot m is equal to m. So this is identity. So m goes to m. So f tilde compose g is equal to ident. And now g compose f tilde of g compose f tilde r cross g of rf is equal to one tensor rf is equal to r tensor f by the properties of tensor product. Okay, so this is audible.
Yes, sir. Audible. Sir, I had to fill a form online and there was a payment gateway problem, so I am late. Please, what?
Okay, no problem.
Okay, sir.
Can you see the screen?
Yes, it is clearly.
Okay, and is my voice clear?
Yes, yes, voice is clear.
Any other noises coming? That's what I'm asking.
I think there the slight sound are coming. This is from device problem or internet issues.
Okay, now tell me, is my voice clear? Is the
Yeah,
other sound is coming?
no, no, it is
Okay,
all
now
right.
okay. Okay, so first today we have started just by recalling the tensor product, that is n tensor n is generated by the all elements of the form small m, which is tensor small n. Okay,
Okay.
so any elements of m tensor n can be written as a linear combination of summation ai mi tensor ni, right?
Yes.
Yeah. Now and we have those following properties. these following properties. Okay,
Okay.
always keep in mind this property. Okay, so basically today we are trying to prove the following. If M is an R module, sorry, M is an R module, then R tensor M isomorphic to M as R module. This is what we want to prove. Okay, you understand?
We want to prove this theorem. Okay.
If M is an R module, the R tensor M isomorphic to M as R
Sir,
module. Okay.
1 minute. I am writing down the copy form. Just 1 minute.
Yes, yes. Okay, please.
Okay, I am writing down the statement. Okay, sir. You can continue.
Whenever you finish writing, just let me know.
Okay. Yes, sir. Scroll down the page.
Okay.
Sir, this line R tensor m to f tilde, this function here, is it to define z such that m goes to r cross m?
Oh, no, no. Oh, that map GM to R tensor M. That may be what I'm talking about.
That is m goes to 1 cross m, right?
Are you talking about this map?
Huh, huh, huh.
No, no. What is cross? M goes to 1 tensor M.
Huh, cross, okay. So f tilde compose z is equal to
Basically, we need to check that if tilde compose G is equal to identity or not, and similarly G compose F tilde is equal to identity or not. These two we need to check, and these two we
huh,
have to put an instance.
okay, okay.
Yeah.
Okay, sir.
Okay. Okay. So first, let me know. Do you understand the proof? I mean, whatever we can. Do you understand? If you have any doubt, just tell me. Okay. I hope you understand the proof.
Okay,
Yeah.
okay.
No, if you have, if you don't understand the proof, tell me. I mean, don't be silent.
Sir, actually, showing this type of isomorphism in R tensor M, it is isomorphic to M. We need to find bijective function, as so far we have did in others isomorphism.
Yes, yes. If the biject, no, no. I mean, the point is in other isomorphism. Suppose you produce a function, and then you need to check the injectivity and surjectivity. Okay. I mean, you can check kernel of that map is zero or not. But in case of tensor product, it is not possible to check the kernel. Okay. So that's why you need to always find the reverse map in order to show the composition of the both whether identity or not. Okay. Here you can't really check the kernel.
Okay, that is the point. How can I did not check the kernel because it is not defined in the.
No, no, kernel is defined. I mean, kernel is defined as per. I mean, kernel is obvious. I mean, kernel is equal to all those other R10 equal to zero. But the problem is that we are in tensor product, right? So,
Yes.
and suppose A tensor B equal to 0. Okay, this means what? This means A comma B belongs to that relation. I mean that submodule generated by those relation we have discussed about on the last Friday. Correct? There are four relations, and any quotienting out by those elements is the submodule generated. We are taking the quotient, right? So AB belongs to that submodule capital D. Okay. So that's why it is difficult to check what is actually A tensor B. So that's why, I mean, in a particular problem, it is maybe easy to check, but in general, it is difficult to check. That's why
Hmm.
in tensor model, we usually try to avoid checking the kernel zero or not. Okay.
Okay. That is why you need to consider the reverse function also.
Yes, yes. Or not also, it's always.
Uh,
Okay. So do you understand proof? This proof? If you have any,
yes.
tell me. If you have any doubt, tell me. Don't hesitate. Don't hesitate. If you have doubt, please tell
Uh,
me.
okay, I'm saying almost I have understand. See, once again the A tilde compose Z and G tilde compose A.
So basically, F intercompose G, I mean, these are identified by the definition of tensor product and by
Hmm.
definition. So,
Yes, sir.
so shall we move to next problem?
Hmm.
Okay. So now we will prove the following. The thing is, tensor product can be taken in any order. That is, M tensor is isomorphic to N tensor. Okay. Obviously, as R module. So first tell me how you approach this problem. Don't hesitate. Whatever way you are thinking to problem approach this problem. How first you approach this problem? How you will approach this problem? Don't be silent.
Yes, I'm thinking, sir.
Okay. Take your time. Okay. And let me know.
Sir, can we use the this theorem, this R cross A module isomorphic to A?
No, no, no. No, no. What are we talking about? You don't need to use any theorem. You can directly do it. There is no need to use any other thing. Okay, just try to construct two maps from M tensor M to N tensor M, and then also try to construct them in the reverse direction. That's all you need to do. Okay,
Okay.
understand? No need to use any theorem. Tell me how you construct the maps. Think about it and tell me.
Sir, if it is commutative, then the map small m tensor small n goes to mn.
Hmm. Sorry, tell me one thing.
Small m tensor small n goes to mn.
I mean, look, you need to construct mass from m tensor n to n tensor n. So what is mn?
Achha.
I mean, m and n are two different modules. So mn does not make sense, right? Correct?
Yes, yes, yes.
Yeah.
The form of the element of the m tensor n, and I have to define a function such that it carries the element of this tensor to this tensor. What is the form of the m tensor n? uh,
No, no. First of all, there is no. I mean, come on, look. M tensor is an element. It is the element. I mean, this is the element. There is no point. There is. It does not make sense asking the form. M tensor n is an element of the module M tensor n. Okay.
yes.
So there is no point of form. This is the element. One element look like this. That's all.
I mean to say I have to construct the function which carries this element to the n cross m element, such as it should be well defined,
Yes.
and reverse function also exists for that.
Yes. So what is the obvious match?
I identity map, no.
Yeah.
Identity map, because m cross n is equal to n cross m. M.
Mhm. They look this. Understand?
Yes, yes.
I mean, this is the map. This is obvious map.
Huh.
Now first check that this map is well defined or not.
Yes.
So for well defined, what you need to do? You need to first consider the map from n cross n to n tensor n.
Hmm.
Check that is it bilinear. If it is bilinear, then the map written on the tensor product is well defined, right? Correct?
Yes.
Okay. So if you have any now issues understanding,
They are mapped from m cross n to m tensor m. Okay.
right side we need to always put on the right side. That's it.
Yes. Yes. No. No problem.
Okay, you just Think about it. I said back to 100%. So,
ভালো সে পড়াশোনা
আপাতত ঠিকঠাক আছে। আপাত আপাতত ঠিকঠাক আছে। ওইখানে সাবু খাচ্ছি। সাবু সাবু ছাড়া কি খাবো আর? আরে না না, অনুমোদন একদম কম, তাহলে অসুবিধা আছে। আচ্ছা, তো ওই ডাল, ওই ভাত ছিল, লাউ ছিল। না না, খায় না। আলু সেদ্ধ ছিল, আলু সেদ্ধ ছিল, পেঁপে সেদ্ধ ছিল, করলা সেদ্ধ ছিল, আর লাউ ছিল। আচ্ছা, নাও। হ্যাঁ, দিয়ে দিচ্ছি। নাও, নাও, নাও। Yeah. So yeah. So do you make yourself clear about the well-defined as a binary of this map?
ইয়েস ইয়েস স্যার
Okay. So this proves. Okay. So this is one directional map, and so what is the? I mean, this is one directional map. So what is the reverse direction map?
reverse direction obviously as it is in n n cross n tensor n goes to m tensor n.
Yeah. Right. Right. Okay. So let's go to the next problem. So moral of the story is you need to construct bilinear map first, then you can only construct well-defined map. And do note one thing, that these isomorphisms, I mean, so this is isomorphism. So tensors can be taken in any order. Okay, but the thing is, it's an isomorphism. But while working some problem, always try to remember the isomorphism map explicitly. I mean, isomorphism is fine, but you also need to motivate mind the explicit mapping. Okay,
Okay.
understand? So also, uh, one thing you may know, that for suppose M, N, P are both are all R modules. Okay, then M tensor N tensor P is isomorphic to M tensor N tensor P. Okay, and obviously you might guess that map is very obvious now.
Yes.
Okay, anyway, I'm not doing the proof because this proof can be done in this manner. Just so I'm ignoring the proof. Okay. Now there is something new. So so now, by the way, tell me one thing. Have you heard those terms, exact sequence?
Exact sequence I have just heard by term. I don't know anything more about
No,
what is it
okay.
definition of.
I mean, term means is it in surplus, or is you have to question about some other source?
Oh, I no sir.
No, no. I mean to say, is it in the syllabus of the exam?
Yes, yes sir.
Is it in the syllabus of the exam, the exact sequence?
You mean yes, exam syllabus of this course?
Yes, yes,
Okay.
yes. It is there, right?
Yes, yes.
Okay, okay. Okay, so Okay, so good. Okay, so one more thing. Suppose F is a map from M to N prime, okay, and
Hmm.
G is a map from N to N prime, and both are linear, okay. R linear means R module homomorphism, okay. This is the R
Hmm.
linearity, okay. Now, so this this, this gives a linear map F tensor G from what to where M tensor N to M prime tensor N given by M tensor N goes to FM, sorry, tensor G. Sorry. So basically, the map is F tensor N, M cross. So this is the map. Okay.
Okay.
So and this is a linear map. First of all, and the thing is, it is a well-defined linear map because you can check the well-definedness first by checking the bilinearity of this map. Then it induces a well-defined map from M cross M tensor to M prime tensor M prime. Okay, understand this?
Okay. Okay.
So keep this notation in mind. What does it mean by F tensor geometry? And moreover, there is one more thing. Suppose F prime is a map from M prime to M double prime. G prime is a map prime, and at the starting we have some map M to N prime, G N to N prime, sorry, N prime. Then the following will hold: F prime compose F tensor. Kindly wait a second, one. Kindly wait. So F prime compose F tensor. Sorry, what? So F prime compose F tensor, G prime compose G is nothing but F prime tensor G prime compose F tensor G. Understand?
Hmm. Yes.
So this is one more.
Lastly it is A tensor G. Okay.
Yes, yes, yes. So tensor of composition and composition tensor. That's all. Okay. There is nothing much to tell about this. But keep this thing in mind. That's the point. So okay, now let's go to the problem. So try to solve this first. So suppose R be a ring, okay, and Ij be to I. Then R by I tensor R by J is isomorphic to R by I plus. So so this is what you need to prove. Now tell me one thing. So first, in order to prove this thing, I mean, so you need to consider explicit maps in both directions, right? So first, tell me which map can be taken. So R by I cross R by J to R by I plus J. We need to define a map. So what the map should be? Think about it first. So whatever the map you choose, do note that in the reverse direction it will give identity after doing the composition. That's the thing you need to keep always in mind. Okay. So now tell me what is the map R1 bar R from R2 bar goes to where? Also, the map you will take, it has to be bilinear. So now tell me, what is the expected map?
It's, sir, it is R cosine over I plus j or I plus j over R.
Sorry, I didn't get you. Sorry.
Yes, the map R by J cross R by J to R by I plus R J or
R,
I
R,
plus.
R by I plus J. I plus J is an ideal, right?
Yes, yes.
So obviously R by I plus J.
Uh,
Now think about, tell me what is the possible map. Take a pen.
it is simply goes to R1 R2.
So means plus.
Huh?
Is it, are you saying in the plus?
Uh, Not plus in multiplication, ring multiplication.
Yeah, fine. Correct. Or on the whole bar. So this is what we were talking about, correct?
Yes.
Okay. So first check that is this map well defined, because the we have in R1 bar R2 bar. So any element might have different image. So first tell that is this map well defined. First check it, is this map well defined or not. If you try first, I mean first check the well defined system. You understand why you need to check well defined at this stage?
Yes, yes.
Yeah.
Sir, it is using the property of coset of ideal. Sir, well defined. I mean, it is sufficient that different element of the domain are mapped to the different.
What did I say? I didn't get it.
Sorry. Sorry. If x two element if x
So
and y x is equal to y imply f of x is equal to f of y. Okay.
no. The thing is, you need to check the well defined not. What do you need to do?
I need to R1 bar R2 bar is equal to if R1 dash bar and R2 dash bar, then that imply R1 R2 bar is equal to R1 dash R2 dash whole bar. Yes,
Yeah.
yes, yeah.
What is
Yes,
it?
yes.
So now what you will do for that? Go systematically.
Yes,
Yeah.
yes. R1 minus R dash belongs to I. Okay,
Mm. Yes.
I uh, and R2 dash belongs to J. Okay, and
Then
okay, they are the ideal of R. Okay, uh, so R1 minus R2 into R2 minus R1 that belongs to I.
there is no point. So basically, so call it this is equal to I. I mean R1 minus R1 dash is equal to small I.
Uh,
R2 minus R2 is equal to small j. Correct. So R1
okay,
is equal to what? R1 dash plus I. R2 is equal to what? R2 dash plus j. Correct.
yes,
Now what do you do? You do
uh,
R1. So R1 R2 is basically R1 plus I dot R2 dash plus small j. Okay. So
okay,
R1 dash R2 dash plus I R2 dash plus j R1 dash sorry plus I j. Okay.
okay,
This element belong to capital I. This
okay,
element belongs to capital J, and this element anyway belongs to I intersection J, right? So this
yes, yes,
whole element belongs to I plus J, correct? So this plus
yes,
what? R1 R2 whole bar is equal to R1 bar R2 bar. Understand?
yes, yes.
So that's so this is all over well defined. It's okay. Now check that this map is bilinear or not.
Yes. Uh, yes, it is bilinear. If I consider R1 R1 R2 into
Yeah, you're right. It is actually bilinear by
yes,
the concept itself. Okay. So what we have R cross I tensor R by J equals to R by I plus J R1. Okay, understand? So this is one dash map. Whatever the reverse map R by I plus J, we need to put R by I.
Yes.
So R bar goes to where you can put R bar tensor I, or as well as you can put one tensor R bar. Okay. So first,
Yes.
so check the first well definedness. Check the well definedness first.
Sir, I'm not getting the point. R bar goes to R. Yes, yes. R tensor one identity. So,
No, no. I mean, R bar goes to R bar tensor one bar. One means one, the one element.
oh,
Yeah. And this is also equal to one bar
one.
tensor.
Okay, okay. Okay.
So now first check the well definedness of this map.
R. So, if we consider R1 bar and R2 bar two different element of domain, and then if R1 if R1 bar is equal to R2 bar, then R1 bar minus R2 bar is equal to uh, zero element.
Okay. So it is equal to small I plus small, correct?
Hmm.
So now R1 bar tensor 1 bar is equal to R2 plus I plus J whole bar tensor 1 bar is equal to R2 plus J bar tensor 1 bar, right? Left side
Yes,
I bar will go vanish because we are in I, and this is equal to R2 bar plus J bar tensor 1 bar, right?
yes,
And this is equal to R2 bar tensor 1 bar plus J bar tensor 1 bar. This is equal to R2 bar tensor 1 bar plus 1 bar tensor J bar is equal to 0. The whole thing equal to 0. So only remaining thing is R2 bar tensor 1 bar.
yes,
So so these are the maps of two directions. Now check that obvious one, that composition of two directions are identity.
yes, yes.
So first, do you understand the whole proof?
Yes, yes.
So you know, so you know about the ring Rx, right? The polynomial ring, correct?
Yes, yes.
Prove that Rx tensor isomorphic Rx. Take your time, think about it first.
Sir, it is sufficient if I can show that Rx tensor Ry is it isomorphic to Rx, uh, Rx Ry. I mean xy third bracket xy term can be split into R small a R x into y.
Yeah, right. Okay, that's fine. Okay, so what is the math? I mean, whatever you said is correct. First, try to write that's not explicitly and let me know.
Sir, I'm thinking.
Yes, yes, take your time.
Yes, yes, sir. It can be shown that Rx generated by ideal X, it is isomorphic to R, and similarly Ry ideal generated by Y isomorphic to R.
Okay. So, so fx tensor gy goes to fx gy. This is one direction map. Okay.
Yes,
Second direction map we need to define rxy goes to rx ry. How to define this map? So any element is basically the linear combination of summation ai hm xi yj. Okay. This
yes,
goes to summation ij aij xi tensor yj. Okay. So this is the map of the reverse direction. Understand?
okay,
Now you can check that these two maps are inverses of each other. I mean, I'm not checking it, but I hope you can do it as well. You understand the point?
yes,
Okay. So,
sir. Is it uh, shown in that uh, using those theorem we have already done in this class, rather from defining the explicit form of this function, whatever you done now
yet you
using
will.
only theorems.
No, no, can you please repeat? Actually, I didn't get your point.
uh, Actually I am saying, can it be shown in such a way that we directly use the theorem, whatever theorem we have done in the class, rather from defining this map explicitly.
No, 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 no. You need to define maps. Without doing maps, it is almost not possible to show isomorphism in tensor product. Okay.
Okay.
That is the problem with the tensor product. So you need to
uh,
go explicit maps always. Okay.
Sir, tensor product, we have a paper in semester, in this semester, named tensor calculus, that is far
That,
different from.
that, that is different thing.
uh,
I mean that is this comes in dynamics, I guess. That's
uh,
separate. That's separate thing. And it is separate thing.
okay. I think names name are same almost, so.
Names are same, but there is really no connection. Maybe connection, but sorry, I don't know.
Okay.
Okay. Okay, so okay, so okay, so now tell me one thing. So that if GCD m comma n is equal to 1, then z by mz tensor z by mz is isomorphic to 0. Sorry, it is equal to 0. GCD m n equal to 1, then z by mz tensor z by mz equal to 0.
Sir, it is it can be shown that it is equivalent to uh, uh, z by mz cross z by nz by last theorem. Whatever we have proved that r quotient I tensor r quotient j isomorphic to r quotient I plus j.
Ah, yes, fine.
Then mz plus nz, it can be written in the form m plus nz.
Yes. Then
Then then I have to show I have to show this is a zero. Sir, yeah, zero means zero tensor. Okay.
ah, yeah. So till now you understood that this is equal to z by mz plus nz. Right now you need to check it is 0 or not. Correct?
Yes, yes.
Noted. We have GCD mn equal to 1.
Okay. Yes, yes. There exists Bayesian identity. There exists Z from M S plus N R, where S R belongs from Z, that equal to 1.
Sorry,
Yes, sir.
please repeat.
Uh, uh, as it is, GCD is M N is equal to 1, so there exists integer R and S belongs from Z, such that M R plus N S is equal to 1.
That's fine.
So ideal if content identity content these elements, so whole thing turn into be ring Z.
Perfect. So yeah, it's fine. You are getting it correctly. Yes. Also, without doing anything, you can also prove this. I mean, without using these facts,
Hmm.
you can directly prove how. So look, I mean, so you take, I mean, first of all, so only you need to check 1 bar tensor 1 bar equal to 0 or not, right? Because any
Yes,
event for both sides is multiple of this, only you need to check 1 bar tensor 1 bar, correct?
yes, yes.
So 1 bar tensor 1 bar is what? So 1 can be written as MR plus NS whole bar, tensor 1 bar. Okay, so
Okay.
um, huh. So RM whole bar tensor 1 bar,
Yes, it is property of the.
yeah, tensor, and this part is 0. So this whole part vanish and it is equal to n bar ns bar tensor 1 bar, and this is equal to s bar tensor n bar equal to 0. So whole thing equal to, you understand?
Yes, yes.
Yeah. So more or less these are the way for approaching the things regarding tensor products. Okay.
Hmm.
Now, okay. So now since since the exact sequence is also clever, so is it fine if we go to the exact sequence now? Because tensor product, there is some connection between those two also. That is not more problem. Okay. So okay, so let's go there. So you don't have any idea of exact sequences?
Yes, yes, sir.
You don't have any idea of exact sequence?
Mhm.
Oh.
No.
So uh, kindly wait for 2 minutes. The definition goes as follows: a sequence of a module, a modules, and leave over a modules, put it R modules. A sequence of R modules and R homomorphisms. Homomorphism means module homomorphism, right? Okay. First, let me write it down. To be exact, at mi, if image of fi is equal to kernel of fi plus 1, the sequence is exactly if it is exact at each mi. So the theorem is, sorry, the definition is as follows. Definition is quite vague, but there is nothing really. So suppose you have a collection of R modules, okay, and you have a collection of homomorphisms, like fi from mi minus 1 to mi, fi plus 1 to mi to mi plus 1, and left side goes to infinite and the right side maybe goes to infinite. Okay, finite, infinite, whatever it is that is. Then the sequence is said to be exact at each mi if image of the previous map is equal to kernel of the next map. Okay, these are definition. Exact means image of previous map.
Sir, exact at mi for all I.
No, no, some I. No, no,
Okay, okay.
it is I. Okay, so it is said to be exact at this portion if the incoming map fi its image is equal to the kernel of the outgoing map. Okay, if
Hmm.
this happens at particular points, then this is exact at mi, and if for all mi is exact, then this whole sequence is said to be exact sequence. Okay, that's all. There is really, I mean, that's all. Yeah. Okay. Do you understand definition?
Okay.
And also, so tell me one thing. So sometimes we may write like let m1, m2. I mean, these are some notions actually. That's why you need to know. So sometimes it may be written like m1, m2, m3, m4, f1, f2, f2 is exact. Means you need to understand that the image of the previous map is a kernel of the next map for each of this point m1, for each of this m2 and m3. Okay.
Okay.
Okay. And one more thing is that um, okay. And one more thing, let 0 belongs to m1 goes to m2 goes to dot dot dot. Suppose f1, f2. This is exact means f1 is ejective map. I mean, for rest of the portion, exactness definition goes as well, but it is exact at this point m1. This directly implies f1 is exact. Do you understand? I mean, sorry, f1 is
Yes,
ejective. Sorry.
yes, yes, yes. Yes.
Yeah, and similarly, if suppose m1, m2, 0, this is exact means f subjective. Okay,
Hmm.
and any exact sequence and nothing, any exact sequence of the form 0 goes to m and b comma 0 is said to be short exact sequence. Okay, so these are some basic notions. Understand? Now, okay. Now there are some facts connected to tensor second. So let be an exact sequence. Okay. Now the question is, so the question is, suppose we have a given tensor, we have a given exact sequence, then after tensoring with some given module, will the whole sequence be exact or not? This is one question. Okay, I mean, so this is one thing we need to understand. Okay. Now the point is that, so for that, first we need to suppose we have this map f and g. Okay, sorry, and then what is this map? F tensor 1, g tensor 1, right? So we need to check whether F tensor 1 injective. This is what we need to check. Also, we need to check G tensor 1 surjective. Also, we need to check kernel of G tensor 1. Is it equal to image of F tensor 1? This is what we need to check, right? Tell me. This is what we need to check, right?
Yes, here Q. What is Q?
Use any module.
Okay, okay.
So question is that suppose we have given a class sequence. After tensor with some another module, will the resulting sequence be exact or not? This is the question, okay?
Yes.
So for that, what we need to check? We need to check that if tensor 1 is injected or not, G tensor 1 is injected or not, and corresponding kernel of G tensor 1 is equal to image of F tensor 1 is happening or not. This is what we need to check, correct?
Hmm.
Okay. So the theorem is as follows. Theorem is for given this thing, only this part will be exact. So this is a theorem. So the point, sorry, say F tensor. So point is F tensor 1 may not be injective, right?
Yes, sir. Repeat.
Sorry, please repeat. Please repeat. Yeah, tell.
Please repeat, sir. M
The
theorem.
theorem is as follows. Suppose 0 m n p, 0 is the exact sequence, okay?
Hmm.
Then m cross q to n cross q to p cross q, this sequence is exact. I mean, on just this 0 will vanish here, okay? So that means what? The F tensor 1 may not be injective, correct?
Yes.
Yeah. So this is a theorem. This is a theorem. This is the exact. So first thing, first one example I will try to show that F tensor 1 may not be injective. So this is what we need to do first, correct? Understand?
Yes.
So consider the following: the 0 to z. This is a 0. It is an exact sequence or not? First check.
Yes, sir. Z cross Z to Z.
No, no, it is not z cross. It is z to z multiplication by 2.
Okay.
check that this sequence is exact or not.
Mm, no, it is not exact because it's not injective map multiplied by 2.
No, no. What you said just now? What I said just now?
Hmm? Yes.
What you have said just now?
I have said that as it is told earlier that if we start 0 and if we show that the first map is injective, then we can say that this is exact.
I mean, exactness means, first map is injective or not. So Z multiplied by 2 is injective or not.
Suppose
I mean, it just what, when there is no point of thinking, you write down whatever you are thinking, you will get the answer automatically. Write it down in order to check if it's exact at each and every point or not, right? First, take your time and write it down.
yes, it is. Sorry, yes, it is injective.
Yeah.
Yes, yes.
One second, wait. So, and is exact in the other question. Okay. Now,
Yeah.
do this thing. One second. So this is another map we will getting by doing tensor through Z2. Now check, is it injective or not? I mean, do you understand what I'm trying to do? Basically, do. The thing is, so if we have a given expression of this form, then only the last three part will form an exact sequence. So basically, f tensor 1 may not be exact. I'm sorry, f tensor 1 may not be injective, right? So now
Yes.
we are trying to get one example where f tensor 1 it may not be injective map. Okay. So this is the map we're taking. 0 goes to z2, z2, z by 2 to 0, and 0 goes to z. So now we are tensoring 0 goes to z, tensor z2 to z and z2 and multiplication by 2 cross 1. Now check this map is injective or not. Okay.
Okay.
First try, then let me know. Are you able to check whether this map is injective or not? Are you able to check whether this map is injective or not?
Yes, sir, trying.
Yes.
Yes, it is injecting.
Okay. You are getting this to inject, right?
Yes.
Okay. So, what is the map? So, map is n tensor x bar goes to 2n tensor x bar, right? This is the map. This is this map, correct?
Yes.
Now, 2n tensor, this can be written what? I mean, first of all, tell me how you are getting injectiveness, injectivity. First, tell me this. How you are checking this map injectivity?
I'm checking the kernel of this.
Okay, so I have already told there is no point of checking kernel because kernel is checking kernel is extremely difficult task. Since there
Oh, okay, okay, sir. Okay. Oh, yes, yes. In injective, take two element two n1 x1 and two n2 x2. Okay. Then this should be, if this should be equal to n1 x1 bar is equal to 2n2 tensor x2 bar, then should if it imply uh, n1 is equal to n2 and x1 is equal to x2, then injectivities.
repeat again.
I have take two element in the form 2n1 x1 bar and 2n2 tensor x2 bar, and equating them.
How you will equate? I mean, you are checking the injectivity, right? Okay.
Yes,
Okay. So,
yes,
then
from
what it?
here uh,
Yeah, tell.
from your as it is uh, take single side to the both.
Why? It is x2 bar here and x1 bar here. So how will take equal? I
Hmm.
mean, you are taking this is equal to 0, right?
Yes, yes.
Okay then.
And then using some property of the tensor, my aim is to see whether n1 is equal to n2 and x1 is equal to x2 or not.
But directly from TensorFlow you can't go with the kernel. That's what I said. I mean, you can't check whether it is actually exact one just by looking this way. In TensorFlow, it's not possible. Only you can do, you can make a reverse map, show the composition identity. That's the only way to show. I mean, if you show that G compose F is equal to 1, then F is
Oh,
injective. That's the,
I cannot proceed further from this explicit form of this tensor product. Okay.
yeah, that's fine. So, look, first of all, we have, okay, so that's possible. Okay. So, observe one thing, is 2 and tensor x bar, right? Correct?
Yes.
This can be written as what? X tensor 2x bar, right? And we have z2, where is z2? So, it is 0. So, this whole thing is 0, correct? So this is a
Uh,
this is
uh,
this map is a
yes, yes, it is the property of the tensor. Okay, huh, huh.
yeah.
Yes.
So this map is a zero map actually.
Huh,
But
yes.
let's say for Z2 is isomorphic to Z2, correct? So it is not
Huh.
injective, right? Understand?
Yes, yes.
Is it clear?
Yeah, yes, yes, yes. Oh, okay, okay. Hmm. Okay, okay.
So that's all. That's what it is. That tensor product. I mean, the tensor product may not keep the injective map to injective map. Okay. So that's the problem. So that's why this theorem is that on the right side three terms are making the exact sequence. Okay. So that's why we discussed the first term. Do you understand now? The first F tensor one may not be injective. Understand now?
Yes, it is an example of that.
Okay. So this is one part, and so now tell me one thing. Okay. So I mean, so this is that's all for the tensor product actually. One second.
Sir, sorry. In order to prove that Jordan canonical form and rational canonical form, up to what extent it should be enough to understanding the proof or argument in. I
Okay.
I I,
The first
I have.
first
Uh,
one thing
yes,
that what you want to prove using the Jordan rational. What you want to prove using those.
yes, I'm telling 1 second. Okay. It is in the form where uh, the matrix is not diagonalizable, but we want to put them similar, most similar to the diagonal form, where the eigenvalue are not regular.
Ah, yes, yes, yes. Please repeat. That's what you have said.
Yes. In Jordan or rational canonical form, we have done this diagonalization process where the eigenvalue are geometric and algebraic multiplicity are equal. I mean they are regular. Then we can easily put them in a diagonalizing form. But problem is where when the eigenvalue are not regular or not sufficient eigen vector to the corresponding eigenvalues, then and these tools are used to put the matrix in similar form of the diagonal form.
All right. Okay. You can you please repeat again?
Yes,
Can you please repeat
yes.
again? Please repeat again.
Uh, okay. I am telling just 1 second. I am telling that when when linear transformation or matrix have not sufficient eigenvectors are corresponding to eigenvalues, then we cannot put in directly in the form diagonalizing form.
Oh, okay. Yes, but then you carry on.
Uh, but uh, but uh, uh, but it is a procedure to extend the most similar of the diagonal form as much as we can.
No, no, no. Diagonal form is different. Jordan form is different. Rational form, something coming from Jordan. Sorry, Jordan form, something coming from rational form. But anyway, these three things are different.
Okay.
I mean, these are not really similar. Matrix diagonalization, there is some condition, and any matrix can be put in Jordan form. Any matrix can be put in rational form. Okay? So there is direct no condition about Jordan and diagonal form. Yes, I mean, if there is some, I mean, there are certain condition obviously such that the Jordan form becomes a diagonal form. So that's the one condition you may think, but there is no direct connection between this because you will go through the proofs. These proofs are entirely different. Okay, and these proofs are completely independent of each other. So I mean, there is no direct connection. Okay,
Okay.
but point is, if two matrices have same Jordan form, then they have same diagonal form. Because same Jordan
Okay.
form means those matrices are similar matrices, so that's the same diagram. That's the thing. Okay.
Okay.
So any other questions?
Yes.
Any other questions?
Any other question? I mean, uh, after Jordan and rational canonical form, there are what are the extent of this linear algebra? I know SVD because there was a paper in graduation where
What is
some
what is
uh,
SBD? What is SBD?
it, singular value decomposition
Okay, yeah, yeah.
and polar decomposition of a matrix. This was just surface to this portion, and we had to do just mechanical calculation to put in form on standard form or just surface to the concept only.
Actually, I was singularity calculation because I no because I never known. I don't need anything regarding singularity composition in but that's why I don't know about singularity composition.
Okay.
Okay. But one thing is that in rings, in general module theory also, sorry, in module for PID. Okay,
Hmm.
so tell me one thing. So that rational canonical, Jordan canonical, you have read on the context of module over PID, or you have read in the matrix theory?
Okay.
No, no. Tell me one thing.
Oh,
As of
sorry.
Jordan,
repeat.
Jordan rational, those things you have read in the modular PID portion, or has it been taught to you only in matrix portions?
Okay.
No, no, it is not okay. I'm asking question. I'm asking the
Uh,
question.
no,
You are,
I have not, I have not studied yet the module over PID.
okay, okay. Okay, so anyway, the point is that I mean, definitely will be. So the point is, those Jordan rational canonical form, those things comes from the module over PID context. Okay, so whenever you read the module of PID, the same concept will come there. Then there are some useful application like suppose you have one second. Suppose you have some matrix satisfying this form a square equal to a. Now you need to check up to similarity how many distinct matrices are there.
Yes, yes.
So in
This
order to
type of problems.
have a problem, those Jordan rationale will be helpful. And also possibly matrices you will consider above of MNZ right now, right? But whenever you look at module over PID, you may consider MNQ or MNF or MNC2, C3, those type of things. So that's comes in model theory question. So that's all. I mean, yeah, that's it. Singular decomposition I really don't know. Okay.
And Smith normal form here in the syllabus there are Smith normal form, and that is a finitely generated module and Noetherian condition.
Yes, yes, right, right, right. So look, everything is modular PID, and most probably the modules are taken in finite and finitely generated. Sorry, finitely generated. Then they see easy for the calculation. Okay. So anyway, I mean, yeah, it's finitely generated. But anyway, if you look at the damage code, the Smith
Hmm.
normal form, they calculated it over any type of PID. There is no
Okay,
particular condition they chose, no condition they chose. Okay.
okay, okay. Uh, Sir, do you, determinant. I want to know about the determinant we have learned up to class 12. It is a mechanical computation of a matrix, sum to assigning a real value to it. But what what are there? I have read that there are two or three equivalent definition of determinant. Yes, I want to know
Ah,
rigorously and its geometric interpretation and what is role in the development of subject.
okay. So okay, I don't know about the role and development. Okay. And there, I also don't. I mean, I forgot the human interpretation also, but there are some. There are three equivalent definitions.
Okay.
So, do you have the book schema? Of course, you have the book schema, right?
Yes.
So, in schema, there is a chapter. In algebra book, there is a chapter of determinants, and
Okay.
he started with that with different definition of determinant, and then landed with the usual definition of determinant. Can you remember? I mean, if you don't read the chapter, then read it.
Okay. Okay.
He has started with some other definition of determinant, so concept involving SGN, SGN and all. Okay. Then he landed with the usual definition. Okay.
Okay.
I mean, so those Laplace expansion thing and all. Okay.
Yes. Yes. Yes.
But anyway, I don't know that about geometry interpretation. I don't know.
Okay. Okay.
Okay, so the next live session will be on next Friday. Okay.
Okay. Okay, sir. Sir, one question, if you don't mind, it is not relevant to academic question. Uh, are you, sir, are you doing a postdoc? Okay, okay, sir. PhD, which year, sir?
Second year.
Oh, okay. Institute?
I remember.
IT Mendes. Okay, okay, sir. Okay, sir. Thank you.
Okay. So the next live session will be on Friday, 7 to 8 p.m. Okay.
Hmm. Okay, sir.
Okay, I'm leaving the call.
Okay. Good.